Welcome friends. As per the request from our viewers, some of our subscribers requested for the load flow radial distribution using BIBC BCBV method. So I am here to present you radial distribution method using BIBC and BCBV. Let's begin. I have already opened the Matlab file. First of all, we have to understand the theory behind it. The radial distribution load flow can be performed by using forward backward sweep, that is using power summation method as well as BIBC BCBV method. And before going into this method, I want to share one information that as I have already posted the video on power summation method, so please go through that video before going to this one, because the many things are similar which I am going to skip in this video. In this method, I will be explaining that BIBC, that is bus injectant to branch current matrix, as well as branch current to bus voltage matrix. Let's understand with an example. Here is the 6-bus system. So in the 6-bus system, there is a 5 branches, as we know. In any radial distribution system, the number of branches is 1 lesser than the total number of buses. Here we have to understand I1, I2, I3, I6 are the loads of each buses, and B1, B2, B3, B4, B5 are the current flowing through the each branches. So in this method, we have to find all the load in terms of current as well as all the branch flows in terms of current. The load in terms of current can be found using formula involving current, voltage and power, that is complex power. And after finding the current, the branch current can be found using KCL, that is Kirchhoff's current law. In this figure, the B4 will be I5, likewise B5 will be I6, and B3 will be I4 plus I5, B2 will be I3 plus I4 plus I5 plus I6. And likewise, we can find all the branch currents by using KCL at respective buses. And that can be modeled in the matrix. This matrix is known as BIBC matrix. And one special characteristics of this matrix is this is an upper triangular matrix. And order of this matrix is, if there are n number of buses, then order of this matrix is n-1 into n-1. This is involving all the branches and all the current except source. Load, if there is load at source, then we have to skip that one. That is, in this figure, if there is load at substation, that is I1, in that case also we have to skip I1. Now we can go to the BCBV matrix. BCBV matrix can be found using KVL. In this figure, in BCBV matrix, we have to find a drop between all the buses from source only. That is, in the given figure, if we are going to consider about bus 2, then we have to consider drop from source substation to bus 2. If we are going to consider bus 6, then the drop should be considered from substation to bus 6. That is, if you can calculate those drops, then the bus voltage can be updated by subtracting those drops from substation. That is 1 at an angle 0 minus that drop will be equal to the voltage of respective bus. In the given example, the bus voltage of bus 4, that is V4, can be calculated as V1 minus B1 Z12 minus B2 Z23 minus B3 Z34, and the drop will be equal to the V1 minus V4. Order of this matrix will be also n minus 1 to n minus 1. The BCBV matrix calculates the voltage drop between source to the corresponding buses, that is from source to second bus, third bus, and so on up to the last bus. For feeding the load of bus 2, from which branch the corresponding current should flow. That is in given figure. For feeding the load of bus 2, the current will flow through branch 1 only. When we consider bus load of bus 5, then for feeding the load of bus 5, the current must flow through the B1, B2, that is branch 1, 2, 3, and 4. Likewise, we can find the BCBV matrix. And here we see that del V, that is voltage drop, can be calculated by using BIBC matrix and BCBV matrix, that is BCBV matrix into BIBC matrix into current injection at each bus except source. That can be simplified as del V is equals to DLF times current injection matrix. Now, first of all, we have to read the configuration, physical parameter, loads, compute BCBV matrix and BIBC matrix. That can be directly from the network topology. And after that, we have to assume the bus voltage of each buses to be 1 at angle 0. And we have to compute node currents as I equals to P plus JQ by V conjugate. After that, we have to compute del V using BCBV into BIBC into node injection. Then we have to update the voltages. That is, voltage of each bus can be found by 1 minus del V. After that, we have to compute the branch real and reactive losses. That is, P loss is equals to B square R, whereas Q loss is equals to B square X, where B is the branch current. And we have to go through the iteration until we have error less than the specified one, that is tolerance. And when the load flow is converged, we have to calculate total losses as well as node voltages, display the result. Now let's go to the Matlab program. Here I have taken the example of IEEE 33 radial bus system. And as I have already told that before going to this method, that is BIBC and BCBV method, first of all, you should go through the power summation method, which I have already uploaded in my channel, so that we can understood easily. Here all the things are similar, but we can see that there is a slightly difference between power summation method and BIBC method. That is, here we have to calculate BIBC and BCBV matrix. Here we can see that in this method, I have used two functions, that is base configuration BIBC BCBV as well as distribution load flow BIBC BCBV. First of all, I want to go to the base configuration one. Here all the things are similar up to the finding of N matrix, and only two things are new here, that is finding BIBC matrix as well as BCBV matrix. Let's see the diagram of IEEE 33 bus test system. Here I want to revise the N matrix once again. N matrix gives us the information of interconnection of buses. That is, the order of N matrix is N into N, that is total number of bus to total number of bus, and it consists of 0 and 1s only. And now here we can see that the row 1 has all the values equal to 1. In row 1, each column corresponds to the value 1. Why it is so? Because the row tells us the information that for the feeding of power of which bus, it must flow through bus 1. The feeding the load of bus 1 also, power must go through bus 1, as well as feeding the load of any other bus also, power must go through the bus 1, that is source 1. In second row, column 1 has the value 0 because for feeding the load of bus 1, power do not have to flow through the bus 2. But except 1, the feeding the load of every other bus, including itself also, that is load of bus 2 also, power must flow through the bus 2. So in second row, except first column, all the values are 1. Likewise, when we go through the columns, we see that in first column, only row 1 has the value 1 and all others value are 0. That means it shows that for feeding the load of bus 1, the power flow through bus 1 only. And for feeding the load of bus 2, power flow through bus 1 as well as bus 2. Likewise, for feeding the load of bus 25, power flow through bus 1, bus 2, bus 3, bus 23, bus 24 and bus 25. Row indicates that from that bus, the power flow through which bus, and column indicates that for feeding the load of that bus, power come from which bus. Now, after understanding the NMAT, we can proceed further. That is, now we are going to understand how we can calculate BIBC matrix and BCBV matrix. We have to initialize BIBC as n-1 into n-1 order, and we have to run the loop for each branch, that is from branch number 1 to last branch, that is n-1. And while calculating BIBC matrix, we have to consider, we have to only find the interconnection of branches with that current injections at each buses. Now, as we have already understood and met, for finding the BIBC matrix, we have to use the each row of NMAT, which gives the interrelation between branches and the current injections. So we can think like this. As we know that the power flowing through bus 2 fits the load of bus 2 as well as load of all other bus except one. Now, here question comes, the power flowing through bus 2 must be equal to the power flowing through the branch 1. That is, if we are calculating power flowing through branch 1, then that is equivalent to the power flowing through bus 2. So, how we can interrelate this? This is very important. We know that bus 2 is receiving end of branch 1. We have to just run the loop for each branch, and we have to calculate the receiving end of each branch, and we have to copy that row from NMAT, and we have to add all the currents corresponding to that row having the value 1. I am going to explain once again. When we consider second row, in the second row, all the columns have value 1 except column 1. The power flowing through second bus must be equal to the power flowing through the first branch, and the interrelation between first branch and second bus is that the receiving end of first branch is second bus. That is, in simplified version, we can say that the interrelation between branches and the current injection to the buses can be found easily by finding the receiving end of that branch and copying that row corresponding to the receiving end bus, and by the summation of each current injections corresponding to that row having value 1. So we have to run the loop from 1 to n-1, that is for each branches, and we have to calculate the receiving end of that branch, that is here, and here we have copied the row of NMAT corresponding to that receiving end bus, that is CRRN. Here CRBRN is current branch number and CRRN is current receiving node. Here we have to run the loop from 1 to n-1, that is from 1 to total number of branch, and current branch number is I, and we have to find the current receiving node, that is RN CRBRN, and here we have copied the total row values. Here we have copied the row of NMAT corresponding to receiving in bus number. Now we have run the loop from 1 to n-n, that is from current injection of second bus to last bus number, and the row corresponding to j plus 1, that is for j equals to 1, this j plus 1 will be 2, that is from 2 to last bus. So the row corresponding to that j plus 1. So that copied row, if the j plus 1th column has value 1, that is the branch j fits the load of j plus 1 bus, then corresponding element of BIBC matrix, the value must be 1. Like this, we can calculate BIBC matrix. After that, we have to calculate BCBV matrix. In BCBV matrix, we have to find all the branches through which the power flow to feed the power of that corresponding bus. For example, when we consider the bus 25, for feeding the load of bus 25, power must flow through the first branch, second branch, branch number 22, branch number 23, and branch number 24. And this can be found by using the property of columns in the NMAT. How you can find the corresponding drops from bus 1 to that bus. That is, if we consider the bus 25, we have to calculate the voltage drop between bus 1 to bus 25. That is sum of the voltage drops occurring in branch 1, branch 2, branch 22, branch 23, and branch 24. Now, the column of NMAT gives us the information of that for feeding the corresponding bus, the power must flow through which bus. So here we see that for feeding the load of 25, power must flow through 1, 2, 23, 24, and 25 bus. Since in BCBV matrix, we are going to calculate the voltage drop. So we have to have the information of, so from NMAT, we have the information that for feeding the load of 25, the power must flow through which bus. But for finding BCBV matrix, that is calculating the voltage drop, we have the information power must flow through which branch. That can be easily found by excluding bus 1, and we have to run the loop from bus 2 to the rest of the bus, and we have to calculate the branches, and we have to find the branches using the buses, that is, and if we exclude the source bus, that is bus 1, we can see that for feeding the load of 25, the power must flow through the bus 2, bus 3, bus 23, 24, and 25. The corresponding branch can be found by considering the remaining buses as a receiving in bus and finding corresponding branch of that receiving in bus. So we have to run the loop from 1 to n minus 1. Here we have to run the loop from 2 to n, which we can get easily by adding 1 to this loop, that is from 1 to n minus 1. If we add 1, that corresponds to the 2 to n. So in simplified version, there is two steps. First step is to find the column of and mat corresponding to that bus. After that, we have to find the branches associated with those buses having their value 1 corresponding to that row, considering that bus as a receiving end. So here we have run the loop from 1 to n minus 1, because we have to run the loop from 2 to n. That can be easily found by adding 1 to this loop. So corresponding bus number is I plus 1. Here we have copied the column of n mat corresponding to that current bus number. Again, we have run the loop from 1 to n minus 1. This is for running the loop from 2 to n bus. Now again we have to run the loop from 2 to n, that is except 1 we have to run the loop from bus 2 to last bus. As we have already discussed that this bus we have to consider as the receiving bus, and after that, that is current receiving node equals to j plus 1, and we have to find the branches associated with those receiving in bus, which can be found easily using this one. Now, and in the copied column, the value of the row corresponding to that receiving in node is 1, then the corresponding branch have the contribution in the voltage drop. So we have to copy the impedance of that branch into the corresponding element of BCBV matrix. Likewise, we can calculate BCBV matrix. After calculation of BCBV matrix, we have to go through the another function called F distribution load flow BIBC BCBV matrix. There is only a little bit difference, that is we have to calculate BIBC as well as BCBV matrix. After calculating that, we have to calculate the per unit value of BCBV matrix. As we already know, it is the matrix which have elements as the impedance, branch impedances. So we have to have the per unit value of that. After calculating that, we can also calculate DLF PU as BCBV PU into BIBC matrix. Then just we have to find the complex power injected at each bus in PU. That can be found by complexing P and Q PU. And one thing we have to keep in mind, we have to consider only the load from bus 2 to last bus, that is N, bus N. After that, we have to calculate current injection at those buses, which can be calculated by this formula. Then delta V, that is del V, can be found by DLF into current injection. After that, we have to update the each bus voltages that we have already know. That can be found by 1 minus delta V, del V. And after updating the voltage, new bus injection can be found by using the new updated value. And the tranche currents can be calculated using BIBC into current injection. Now the corresponding active power loss and reactive power loss can be easily found from the formula BS square IR and BS square IX. And the total active power loss can be found by the summation of those branch losses. And we have to calculate the error. Since the voltage obtained here is in complex form, so while calculating error, we have to calculate the error in magnitude as well as the angle. By using absolute function, that is ABS, we have calculated the error in magnitude. By using the function angle, we have calculated the error in voltage angle. And we have calculated the maximum of those two errors, which is the max error. And we have updated the bus voltages and current injections. And when that max error becomes lesser than the tolerance, then this load flow converges. And here also we have given the limit of iteration to the 100, that if this iteration goes beyond 100, then also the loop will be terminated. In that case, the load flow is to be considered as not converged one. So for the convergence, the iteration must be lesser than the 100. Let's run this load flow program once again. Here we can see that the number of iteration taken is 6. So 6 is less than 100. That means load flow converged. Otherwise, if it is equal or greater than 100, then load flow is not converged. And the maximum error deviation is this much. And here is the voltage magnitude. These are the reactive and active power losses in the corresponding branches. That is, the total active power loss is almost 211 kilowatt and reactive power loss is 143 kilohertz. Thank you for giving your precious time for watching this. Hope this video will help you in enhancing your knowledge up to some extent corresponding to the radial distribution load flow using BIBC and BCBV matrix. Thank you for watching.